I will explain you the definition of compact in this video. So before you learn about this compact, you have to know about covering of X. Okay, that is very important. I will explain you what is called covering of X using a diagram. Okay, then only you can understand what I am trying to say. Okay, so first what you have to do is you have to consider a topological space. Imagine this is the topological space and you are going to write the covering of this topological space X. Okay, so within this topological space you can see so many subsets. Okay, so many subsets you can see. Imagine like this. Okay, among these subsets I am choosing some of the subsets. Okay, so if I choose these subsets, okay, I'm choosing these subsets, okay, from this topological space X. And this collection, here you have some of the subsets, right? So this collection is denoted as script A. You are going to say this script A is a covering of capital X. When you can say this script A is a covering of capital X, there is a condition. There is a condition this script A should get satisfied. Then only you can say this script A is a covering of capital X. What is that condition? I will tell you what is that condition. So imagine in this collection you are having some of the subsets, right? I am giving name to each subsets. Okay. So this is A1, this is A2, this is A3, this is A4 and this is A5. Okay, so what I'm going to do is I'm going to find the union of all the elements present in this script A. Okay, now inside this script A you are having elements. Okay, what are the elements? These are the elements present in this script A. Okay, I'm writing that A1, A2, A2, A3, A4, A5. These are the elements present in this script A. I'm going to say this script A is a covering of capital X. Okay. When I will say that, I'm going to find the union of these elements. Okay. These elements. These are the subsets, right? So I'm going to find the union of these elements. When I find the union of these elements present inside the script A, I will get elements, right? So that element should be equal to X. That is, inside X you will have so many elements. That all the elements present in this topological space X should present inside this A1 union, inside this value. Okay, when you find the value of this, you will get some more elements. You will get elements, and that elements is the elements that present in our topological space X. Is that clear? In short, I am saying you all the elements present inside this topological space X should present inside this value. Present inside this. Okay, then you can say the script A is a covering of capital X. I hope you have understood my point. Okay, now I believe that you know what is called covering of X. Now let us pass on to what is called compact. Here you can see the definition of compact. You can see the definition. The space X is said to be compact if every open covering script A of X contains a finite subcollection that also covers X. So here, just before I explained what is called covering of X, I must tell you this also. Covering of X is also called as open covering of X. Open covering and covering both are same. Okay, so here you are considering the topological space X. and you are going to say this topological space X as compact. Okay, so when you will say this topological space X as compact, I will tell you when. If every open covering script A of capital X, I explained to you about one open covering in the topological space X in just before, right? One open covering, that is script A, right? Like that, you will have so many open coverings within the topological space capital X. Okay, imagine you are having so many open coverings like this. Now these are open coverings. Okay, so that is why they are written like this. Every open covering script A of X, every open covering, I am giving name to this. These are the open coverings A1, A2. These are not subsets now, these are open coverings. I told you inside the topological space X, you will have so many open coverings. Just before I explained you about one open covering. Okay, so like that you will have so many open coverings inside the topological space. So every open covering script A of capital X contains a finite subcollection, right? So within every open covering, you will have finite collection of subsets, right? So that will also cover X. Okay, every open covering contains a finite subcollection that also covers X. When you take this A1, okay, this is one of the open coverings. So here you, in this open covering A1, you will have so many subsets within this, right? Okay, so many subsets within this. That subsets also covers this capital X. How you can say this? When you will say it is covering, when you will say that is inside this covering, if you have A1, A2, A3 subsets, then when you find the union of A1, union A2, union A3, you have to get the topological space capital X. Then you will say this A1 is the covering of what? Open covering of this topological space capital X. That is what the concept, right? This is what I come to know from this definition. Okay, so I might be wrong, but this is what I come to know from this definition. Let me read this. The space X is said to be compact if every open covering, what you come to know from this every open covering? Every open covering means inside the topological space you don't have only one open covering, one or two, you will have so many open coverings. Okay, so every open covering of X will have finite subcollection, right? Inside every open covering you will have some subsets, and when you find the union of that subsets, you will get equal to X. That union value equals this topological space X. Every subcollection, every open covering will satisfy this condition. Then you can say what? This X is compact. Is that clear?